I'm here at the Atlantis Royal Towers in the Bahamas, and I thought we could use the bridge between the two Royal Towers to illustrate the operation of a bridge. And remember that a bridge is the predecessor to a switch. They both make forwarding decisions in the same basic way. They take a look at MAC addresses, media access control addresses that they've learned off of their different ports, and they make forwarding decisions appropriately. For example, if you consider the Royal Towers behind me, let's imagine that on one side we have a collection of MAC addresses, of devices. On the other side of the bridge we have another collection of devices, another set of MAC addresses. Now here's the big question. What's going to cause a frame, a layer 2 frame, to go across that bridge? What's going to cause a frame to go from one side to the other side? It's only going to happen if it needs to get there. In other words, if the destination MAC address lives on the other side of the bridge, then yes, the frame will go across the bridge. Well, I said that was the only way. There are some other things that might cause a frame to cross that bridge. For example, let's say that the MAC address table in a switch is full. It doesn't have the capacity to learn any additional MAC addresses. Therefore, if a MAC address lives on one side in one of the towers, and that MAC address has not been learned by the bridge or the switch, then it doesn't know it lives there, and it will forward unknown unicast traffic across that bridge. Something else that can cross a bridge is multicast traffic. Multicast traffic will go across that bridge unless we have some multicast specific configuration that prevents it from doing so. Something else that will cross that bridge is broadcast traffic. Broadcast traffic goes to everyone within a subnet, and therefore it's going to go to everyone on both sides of that bridge. So to sum up, a bridge, it stands between two different collision domains. Each tower in this case is its own collision domain. A collision on one side is not felt by devices on the other side. Traffic is only forwarded normally across the bridge or the switch if the traffic needs to get there based on the switch's examination of the destination MAC address. Other types of traffic that could flow across a bridge include unknown unicast traffic. Maybe a MAC address has not been learned. Maybe it cannot be learned because the MAC address table is full. Or we could have multicast traffic, or we could have broadcast traffic also traversing that bridge.
A switch is going to make its forwarding decision for a frame based on the destination MAC address. And the MAC address is a 48-bit address, and I've illustrated it for you here on screen. 48 bits, that's 6 bytes, isn't it? At 8 bits per byte, that's 6 bytes. And we've got groupings of 3 bytes at the beginning and 3 bytes at the end. The first 3 bytes are referred to as the organizationally unique identifier. This is also sometimes known as the vendor code. So if you were to begin a business that manufactured network interface cards, and you would want to put a MAC address embedded into each of those network interface cards, you would need a vendor code that was assigned just to your company. And then once you had that, you could start all of your MAC addresses with those 24 bits, those 3 bytes. The next 3 bytes, the next 24 bits, would be numbers or digits that you came up with. And grand total, we now have a 48-bit MAC address. Again, the first half of the MAC address, the first 24 bits, or the first 3 bytes, that is assigned to a vendor, and then that vendor, they begin their MAC addresses with that code, and then they make up the last 24 bits and make sure they're unique among all of the network interface cards that they create. And by the way, it's not uncommon for a vendor to have more than one vendor code, more than one organizationally unique identifier, because sometimes companies merge. Sometimes companies just are large and they might need more than one vendor code. That's not a problem at all. It's totally okay for a single company to have more than one vendor code. In fact, as a reference for you, you might want to go on the internet and do an internet search for MAC address vendor codes, and you can get a nice comprehensive listing of what MAC addresses correspond with which companies. And if you see a particular MAC address on your network, maybe you're using some sort of a network sniffer program, That program itself might tell you the vendor, maybe it knows the vendor code, but if it doesn't, you can just reference the vendor code found in that MAC address that you've captured with what you found on the internet. And the way we write out these 48 bits is using hexadecimal notation. It would be far too cumbersome to use ones and zeros to write out the 48 bits, so we do it hexadecimally. It might look like this. We might do something like 5, 8, and then we have a colon, and then we might do 5, 5, CA, just an example MAC address. But I'm showing you that we're using hexadecimal notation, and after every 2 hexadecimal digits, we have a delimiter of a colon. That's one way of doing it. Another way you might see this written is to use a dotted decimal separation. You might have 4 digits. You might see something like 5855 dot CAFA dot 1551. We've got 4 hexadecimal digits, a dot, another 4 hexadecimal digits, a dot, and another 4 hexadecimal digits. Another way you might see it written, instead of the colons as our delimiter after every 2 hexadecimal digits, you might see a delimiter of a hyphen. Different ways of representing this 48-bit MAC address. A switch is going to use a content addressable memory, or a CAM table, to make its forwarding decisions. This table is often referred to as a MAC address table. We can use those terms synonymously, and I've given you a very simplified topology on screen to show you how a CAM table is populated. We've got a switch with a couple of ports. Port 1 connects to PC 1, port 2 connects to PC 2. You see I've indicated the MAC address for each of the PCs, and we began with our CAM table empty. In our table we're saying this port is associated with this MAC address or these MAC addresses. We absolutely could have more than one MAC address available off of a single switch port, because maybe there's another switch attached to that port, and we've got multiple MAC addresses off of that other switch. So no problem, we could have multiple MAC addresses known off of a single switch port. But to keep this example simple, we only have one MAC address off of each port. The way we start to populate the CAM table is when we receive traffic. Let's say that PC1 sends out a frame into the network. Maybe it's doing an address resolution protocol request. And when that frame goes into the switch interrogates that frame, and it looks at the source MAC address in that frame. And it says, based on this frame that I just received on port 1, I have reason to believe that this MAC address lives off of port 1, and the same thing for PC 2. When we receive a frame coming in to port 2, we'll look at that source MAC address and realize that that MAC address lives off of port 2, and as a result, our CAM table becomes populated like you see on screen. Once we have a populated CAM table, the switch can now make intelligent forwarding decisions. Now, when a frame comes in and it's destined, the destination MAC address is, let's say, 5855 CAFA 1551. The switch says that MAC address lives off of port number 1, and it can forward that frame out of port number 1.